in this problem, we're asked to consider whether or not adding 1 liter of each of the respective solutions will result in a buffer solution. Remember, to have a buffer solution, what we need is relatively high and equal concentrations of a weak conjugate acid-base pair. So let's consider adding a liter of each of these solutions together. Now we note that we're adding 1 liter solutions together. So if we have 1 liter of each of these solutions, the molarities are easily converted to moles. Now in this first example, we may be tempted to think we have a buffer because we have 1.5 moles of HNO3 and 0.8 moles of the nitrate ion. It is true that we have an acid and its conjugate base, but HNO3 is a strong acid. So this cannot be a buffer, primarily because HNO3 doesn't exist in solution as HNO3, but rather as dissociated ions. So what really exists in solution is not HNO3, but rather H3O plus, because the HNO3 is going to react with water and the nitrate ion. Okay, so this is not a buffer. So this is not a buffer. Don't forget, we need relatively high and equal concentrations of a weak conjugate acid-base pair. Okay, let's look at the next example. And it doesn't look immediately like this has any chance of being a buffer, but let's consider the reaction that happens. 1.8 moles of hydrogen chloride means we have 1.8 moles of H3O plus because it's going to react with water, and we also have this chloride ion. Now this strong acid is going to react with this weak base. So here's the reaction. We have a weak base reacting with H3O plus, and it's going to give us ammonium ion and water. And we see that if we have the right amounts of each of these, we can potentially achieve a buffer because we have the potential of having both NH3 and NH4 plus. Let's see if it works out in this case. We'll do a BCA table. All right, so initially we have 1.4 moles of ammonia and 1.8 moles of H3O plus that came from the HCl. We initially don't have any ammonium ion, and we don't care about the water because that's a pure liquid. In this case, all of our ammonia is going to react. It's the limiting reagents, essentially. So we lose the same amount of H3O plus, so we're out of NH3, we have a little bit of H3O plus left, and we've gained 1.4 moles of NH4 plus. So what we have after this reaction has occurred is that we have 0.4 moles of H3O plus, 1.4 moles of NH4 plus, not a buffer. But we can see that potentially we could obtain a buffer from this combination if we had more ammonia so that some of it remained behind after all the H3O plus was used, or we had less of the H3O plus. Either way, we would end up having some amount of NH3 and NH4 plus in solution. But in these amounts, this is not a buffer. All right, the next combination, we need to consider the reaction that's going to occur when we have a weak acid added to the same beaker with a strong base. We are going to get an acid-base reaction, so we want to see if after that reaction is complete, if we have the components of a buffer remaining in solution. Okay, we need to use our chemistry knowledge to write out our equation, and it's not as daunting as it may seem. We have an acid, HF. It's a weak acid, but it's an acid. it's going to react with the hydroxide. All of it that's able to react is going to react, and we know that our products are going to be F- and water. If you need to be convinced of that, let's look off to the side. We see HF acting as an acid. It loses an H+. What's left behind is F-. Hydroxide acting as a base. It accepts an H+ to form water. So this is our chemical equation. Let's do our BCA table. Okay, again, we're going to utilize the fact that we have a liter of each of these solutions. So 0.8 molar, 1 liter, gives us 0.8 moles of each of these. So we see that all of the HF and the hydroxide are going to be consumed. So after this reaction is complete, all that's in solution is F-. And that's obviously not a buffer. Let's look at our last sample. So we have 1.6 molar acetic acid, so let's just call it HA, a weak acid. And we have 1.4 molar sodium hydroxide, and we know that the important part is the hydroxide. So we have a weak acid plus a strong base in solution. They're going to react completely. Let's look at our balanced chemical equation. We have our weak acid. It's going to react with our base, and our product is the conjugate base of our weak acid plus water. Let's generate our BCA table. Okay, when these are first mixed and before they react, we have 1.6 moles of HA and we have 1.4 moles of hydroxide. We don't have any of the conjugate base yet, and again, we don't care about water. All right, looks like our limiting reagent here is our hydroxide. All of that is going to be consumed, and that same amount of HA will be consumed. And now we have 0.2 moles of our HA remaining. All of our hydroxide are gone. But if we react our HA with hydroxide, we're going to be generating our conjugate base. Okay, again, you can look over to the side to convince yourself that we have the right products. So after this reaction is complete, we have 0.2 moles of HA and 1.4 moles of A-. Now this is not a balanced buffer, it's a little lopsided, but the concentrations are within a factor of 10 of each other, so we know it is going to be an effective buffer.